Hey, my name is Alex, and I'm going to be showing you guys a bunch of stuff regarding differential calculus. These lectures, basically what motivated me to make these lectures is that when I was learning differential calculus on manifolds, I couldn't really find any online material to help me out of a particular level that was suitable for me, which is, basic knowledge of algebra, n-dimensional calculus on Euclidean spaces, and some kind of basic semblance of the understanding topology and stuff. So that's what we're going to do here. So that's basic. I just named the basics that you need to have in order to follow the course in a more or less reasonable way. And now we're just going to hop right into it. So basically, what we're going to try to do here is we're going to try to develop calculus on topological manifolds, or not develop, but rather go through it and learn it. And first of all, why we need this is if you want to calculate volume or curvature, you're going to need integrals and derivatives. And topology in itself doesn't really provide the necessary framework to do this. So you've got your topological manifold here, and you need to add some machinery to be able to do calculus on it. So we're going to be focusing on this. And let me just give you a couple of examples of topological manifolds. So in R2, you could have a circle, one-dimensional. So you got a two-dimensional ambient space and the one-dimensional manifold here. In 3D, you could have, I don't know how to draw that, but you could have, a sphere, of course, or a torus or something like that. So those are objects that we're interested in doing calculus on. And what I'm going to try to do is, okay, so first thing you need to know is that smoothness or differentiability is not a topological property. So if you have a topological manifold, it doesn't allow to integrate or derive. And we're going to prove that later in the course, but for now you just have to believe me that adding this extra machinery does actually give you some benefits. So what we're going to do now is I'm going to give you a basic definition of what topological manifold is, and we're going to discuss some basics, and then I'm going to give you an example. So I'm going to write down a definition. So definition 1. Or you know what? I'm not going to actually number them because then I'll mess the numbers up. So topological manifold is a topological space with the additional properties. So, with the additional properties of being a Hausdorff space, being second countable, and being locally Euclidean. So, we're going to go through these in case you aren't familiar with them, but if you had some kind of basic course in topology, you should be reasonably familiar with them. So basically, you take a topological space and you impose these 3 additional conditions and you have a topological manifold. So that's how it works. So, Hausdorff, that means that any 2 points can be separated by 2 open neighborhoods, which means that you'll find U1 and U2 open such that U1 intersection U2 is an empty set. Second countable means that there exists a basis, a countable basis of the space. What a topological basis is, you can find on the internet if you don't know, so we're not going to dive into that. So that one we've gone over. And now locally Euclidean, that's the most interesting one that actually characterizes These are more formal, and number 3 is more fundamental in a way. So what locally Euclidean means that I'll write this down. So 3 means that for every p from the, let's call it M, let's call a topological manifold M. For every p from M, we find an open neighborhood U, let's say, from tau M, such that, okay, so we find an open neighborhood, and we find a homeomorphism from U to Rn, such that phi U is open R, is open. Now, what this means is you got your topological manifold here, M, and you've got your Euclidean space here, let's say Rn, and you choose any point over here. Let's name this point P. Then you'll find a local neighborhood U, or there'll always be a local neighborhood that maps to some phi U, which is an open set in Rn. And this phi is a homeomorphism, which means that it's a bijection that's continuous both ways. So phi is continuous, and phi to the minus first is continuous also. So that's the basic definition. If you have any questions, feel free to put them in the comments. We can talk about it. So as you can see, my writing is very poor, but I hope you guys can survive that. And what's next? All right. Now, before we hop into the example, I wanted to give you guys a little bit of a maybe a trivial example, but it's good to get a grip of, use it to get a grip of what topological manifold is. So, let's take Rn. Rn is an n-dimensional topological manifold, and we're just gonna do some Goon work here, and we're just gonna verify number 1. And we know from topology that any metric space is T4, and that implies that it's T2, which is the Hausdorff property. And basically, T4 is just like a stronger condition. That means that if you have any two closed neighborhoods, then you'll be able to find open neighborhoods that don't intersect, that kind of, separate these two. So it's T2 for sure. So number 2, does it have a countable basis? If you take rational, say, I don't know, x1, xn, and balls with rational radii, then you'll get a basis. This can also be proven. That's more or less basic stuff. But number 3 actually isn't really interesting at all, because the local map that is homomorphic to Rn is just the identity in this case. Okay? So this is a pretty nifty way to just, we kind of did some Goon work. We suspected that, of course, it's going to end up to be a n-dimensional topological manifold, but whatever. We verified it, so there you go. So the same way, if you have a more complicated problem, or a little bit more complicated, which we'll look at now, you would do it the exact same way. You would verify these three conditions and then you're done. So let's just look at, okay, so just a little bit of, I'm not even going to write these down, but there's two really important like lemmas or theorems or whatever you want to call it that you should try to prove yourself. If you can't, just hit me up in the comments. We can talk about it or whatever. So the first one is that if you have a topological space that's Hausdorff, a subspace of this space will also be Hausdorff. And also a product of finitely many Hausdorff spaces is a Hausdorff space itself. With of course, considering the induced product topology. So that's one thing, and the same thing goes for second countability. So same thing for subspace. If you take a second countable space, you take a subspace of it, you get again a space that's second countable, and the same for the product. So what did we want to talk about here? So all right, then now let's talk a little bit about coordinate charts. And after we're done with that, we're going to do one example to so just a little bit of terminology so that I don't lose you guys when I talk about these things. So this is our topological manifold M. This is our Euclidean space. And this is a point P. So this neighborhood U is called the coordinate domain. This map phi that maps over here is called the coordinate map, and this open neighborhood here, phi of u, is called those are the local coordinates. Yeah, so actually I think phi I, the components here are called the local coordinates. So that's a little bit of the terminology. A map is called centered at a point. So phi is centered at P if phi P equals 0. Obviously, by subtracting, if it's not centered at a point, at a particular point, by subtracting that point, you will get a map that's centered. Subtracting the value of that point, of course, you'll get a map that's centered at that point. And the pair U, phi, is called a coordinate chart. I'm just going to be writing wonky like this because that's just what I do, so feel free to hate on that, it's fine. But I'm going to emphasize one more time that this is a coordinate chart and this is an important concept. So I'm going to reiterate one more time. You have a P here, and you find the coordinate chart, which is this pair, U, phi, and this basically maps you to your Euclidean space locally. That's the most important thing, that you always have to realize that this is a local thing. So I'm just going to get rid of this and show you the example. And all right, so this example is going to be concerned with like a slightly less trivial topological manifold. So, suppose we are in Rn+1 dimensional space. And then let us define Sn as x is from Rn+1, such that the Euclidean norm, this is how I'm gonna signify the Euclidean norm, is equal to 1. This is of course a unit sphere in Rn+1. And we're going to ask ourselves the question whether this is a topological manifold or not. So again, we need to verify the three properties. So we'll go 1. We ask, is it Hausdorff? Is it Hausdorff? So actually yes, because we've just verified that Rn+1 is Hausdorff. And we know that this is a subspace of Rn+1. So any subspace of a Hausdorff space is a Hausdorff space. So we got that one. Number 2, we want to ask, is it second countable? And again, we use the same argument for second countability. The subspace of a second countable space is second countable from the theorem that I stated before. Again, you can find these online or ask me or whatever. Yeah. Now we're going to move on to the interesting part. Is it locally Euclidean? And I'm just gonna show you how to map it, and then we're gonna verify, or we're gonna look at the maps and see that it actually is a homeomorphism. So suppose that we take U. Suppose that for each I from 1 to n plus 1, we define neighborhoods in the following way. Ui plus is x from Sn such that x, the ith component is positive. And in an analog manner, we'll define, I won't even write it down, but Ui minus is defined in an analog way. And then we define phi I plus minus to be, I just write the vector x here, like this. And this will be, I'll just write how we define this. Phi x1 to xn plus 1. We'll define this as just leaving out the ith coordinate. So we get 1 through xi is left out, this hat means left out in this context, to n plus 1. And so notice how this is, we're actually mapping to Rn, because we suspect this sphere to be an n-dimensional manifold. So that's why we're mapping to Rn right now. So we leave out this coordinate, and we ask ourselves, is this map even continuous? It's a linear map on Rn. Any linear map on Rn is continuous. And any restriction of a continuous map is continuous as well. So like we've basically taken this map that's linear on Rn, so it's continuous, and it's restricted only to the values in the subspace Sn, which is a subspace of Rn plus 1. So we got that, it's continuous. And then the inverse, if you construct the inverse, I'll just write it down like this real quick. The inverse is defined as x1, and then in the ith component you get 1 minus x, Euclidean norm square, like that, to the square root, and plus just n here. So this is also a continuous map. So we have continuity in one direction, continuity in the other. It's bijection, so we have a homeomorphism here. And now, even more importantly, so we've verified that this map is homomorphic. And what we're going to do now is we are going to I'm just going to show you how to imagine what just happened. So what did we do? I'm just going to take n to be 1. So R, 1 plus 1, that's the ambient space that we're working in. So it's this, and we have a circle in here. So U plus, what's U plus here? U plus is just, there's 4 of them. So maybe I better make 4 little icon-ish things here to show you the coordinate neighborhoods, or what are they called? Coordinate domains, coordinate domains. So basically U1 plus is over here. U1 minus is this. U2 plus is here. U2 minus is down here. So basically it's always like the upper plane here, the right hand side here, from the middle here. And basically what phi was doing is it was mapping. So you took, let's take this one, for example. So what phi was doing is it was leaving out the coordinate here, the y coordinate, and going down here and mapping it to this point. So basically, it was playing on the fact that if you make a line here, you will intersect exactly at one point up here, exactly at one point down here. Sorry. And that's how you get. So basically, let me just. I hope that's clear. If it's not, then you can comment. Let me know. And so the point was that these are these 4 neighborhoods, and there's 4 maps. For instance, there was phi 2 plus, which is the map that operates on this part of the circle to map points on the circle to this line, and you can see very clearly that this line is then R1, one-dimensional object. So it maps this 2-dimensional object that's curved here in a continuous way in both directions, 1-to-1 to this line right here. And so that's the whole point. That's the whole point, that we were able to separate the sphere, or in this case, the circle, into 4 different areas on which we could project onto a line. And so we could essentially see that locally, this object is one-dimensional. So that's enough for today. That's what I wanted to cover. So let me know. This is my first lesson covering this kind of thing. So let me know if you liked it, or if it was too fast, or if I glossed over some things. Just comment down below. Subscribe if you liked it. There's more coming. If you guys would like to see some different topics, just let me know. I might want to cover them myself. So just a little bit of an extra, poke and prod from you guys might help me actually do it. And next time we're going to be trying to build up, so at the beginning of the lecture I said that we were going to, do topological manifolds, and then we're going to build up the smooth structure so we can integrate and derive. And so that's what we're going to be doing next time. Moving up, adding that structure, moving on from just a topological manifold to a smooth manifold. So thanks for the attention, and see you guys next time. Ciao.